I'm very curious, and I was telling my wife, like, I'm giving a talk in the compassionate math session, and she says, "What does that mean?" I said, "I think I'm not only am I interested in the idea of it, but the very fact that a group of people are happy to use, a group of mathematicians are happy to use a term that's like not precisely defined at all, and they're perfectly glad to have that be like the organizing principle of the session." So I wanted to actually just ask, especially with a small group like this, I'll come out here too, we can just chat. What do you think it is? Or even just what's an example that you have experienced or thought about of compassionate math? And while I'm waiting for your phone.
Yeah.
I have used it recently in thinking about a person with whom I have an ongoing dispute or disagreement. I love this person, but I don't like him. The distinction between like and love is a major spiritual breakthrough for me, because you don't have to like a person in order to love them. But that being said, being with them is problematic. So the compassionate application of math in this case comes from the notion that the basic ontological unit is not a thing or an object, it's a relationship. Okay, so that who she is and why she's an issue for me is better understand as my relationship to her as a relationship. And when you look at it that way, it's much more dynamic. It opens me up into understanding what constitutes her. It's not just a history of her offenses or our disagreements. It's the composite, or the set, if you will, of all of her relationships that make her who she is, that's in a constant dynamic interaction. And when I look at it that way, it just chills me out and say, who am I to enter that? But instead to appreciate that, sit with it, and I'm actually imagining reaching out to her now.
So do you feel like mathematics, you can say a similar thing about a subject that you can relate to in that kind of way?
Mm-hmm.
I'm just beginning to understand from Ted's reminder, it's not just calculation. It is a way of looking at information and relationships. And so, in that case, I'm just starting over. I took algebra 2, so that's as far as I've gone. And so I'm going back to it now, and I think I can get it, because I just needed to know, well, what is it? And if it was just figuring out formulas and proving things, I got to be in math, but it didn't mean anything. And now that I've related it, now that I understand it in a relational way, I just applied it, and now I can go back to it with much more incentive, motivation, excitement.
I must add that Grady has been joining our group for months now, and he's a great example of a very learned man who doesn't know much math, but is very interested in learning. And so it's like, sometimes we use him as a case study of people we want to reach out to, people who are curious and have the bandwidth to see mathematics as more than just the stuff that we tend to teach young kids, which is sort of somehow the doing of math. And like what we were talking about yesterday, why do we do that? And so at this point, I'm very heartened to hear words come out of Grady's mouth that are actually resonating with some of the things that we talk about. We come to them in a very different way, but apparently is an example of communication or observation, maybe, of the interactions between mathematicians that actually conjures meaning to someone, even though they're not they don't come from the same background. So and I guess in terms of compassion, I'm thinking about eliciting common passions to the other person, by the ways we describe our work. Something that doesn't often happen, for example, in other sessions, even at JMM. This is one of the reasons we wanted to start sessions like this a couple of years ago when we first began this work, because many of us have had, probably all of you, have had examples, opportunities to experience this, right? Where you go into a place, you think you're interested in it, but you don't feel you belong. There's no connection. There's somebody is talking about some things, and they're not even connecting with anyone else, largely. Maybe they want to, right? Let's not imagine that, but somehow the structure isn't there to support that. And so we, making it relational, as Greg is saying, was, I think, is part of compassion that I think for me is important.
I can follow up on that. So yesterday I was thinking, what is opposite to compassion? And many things I could claim, but one of them is being rigid. So it's not what we do, but how we do it. For example, rigid classroom would be like, every semester I teach the same. I just come to class, assign homework, teach a lesson, assign homework, give a test, repeat. Versus when I started introducing creativity, it's more back and forth. So I introduce a small creative assignment, I see how students react, reflect on it, and I adjust that assignment. So we do have an exchange. Moreover, this exchange seems to open up both my mind and my students' mind. So my compassionate approach comes from my Buddhist background. And there are stories there about like self-sharpening circles, devices that are improving on, as you use them, they keep improving. So I think this is an example of that exchange where both sides grow in that exchange. So to me, that would be an expression of compassion. It's two-sided. It's not just me being compassionate towards students. It goes back and forth. It's my take on it.
This is good. I want to see.
Yeah, what do others think? Yeah, please, everyone, has the right here to.
I work very directly with students. I don't lecture. I actually tutor students in like a math lab. So to me, it's very much meeting them where they are. A lot of the students that come here are working on like algebra 1, algebra 2, and have a very spotty background with math. So it's kind of admitting to them that yes, it's difficult, and we can do it.
Mm-hmm.
Maybe reframe it, or slow down, or look at it a different way. Then it's possible, but it is difficult.
Right, validating their feelings about the material, because we all have feelings about the math that we do. We wouldn't do it otherwise if we didn't have feelings about it, right?
Yeah. Well, it's feelings of some kind.
Of some kind, yeah. And they're not all positive necessarily either. We get frustrated very often.
Well, I wanted a kind of a slightly different take on this whole thing. You know what? I'm pretty loud. Let me come out here until I have to hit the button. I'll just talk. The reason I actually came at all to the session, it actually came last year in Seattle first too, and because Irfan invited me, and I didn't know Irfan, and that's why I kind of wanted to wait. But who knows how long he's going to be. It's okay. I'll come. If he's super late, I can catch him later. But I thought it was interesting. I got a call from him. I live in Idaho, so like I'm in the Marines. He called me like 4 years ago. We talked. I didn't know him at all. He just out of the blue. We talked for like 2 hours because he felt, and I'm maybe paraphrasing. He should say it maybe obviously better. But what I remember him telling me is an experience where he felt like math was rejecting him because of his understanding, his way of thinking about the continuum. And he felt like it didn't make sense, and he couldn't, his own imagery and his own ideas, he couldn't figure out how that jived with what he was supposed to be thinking. And then he had this revelation by learning about nonstandard analysis, where he oh wait, he actually got to see that you can have a saturated continuum with infinitesimals in it. Well, that's how I've always thought. And he read a paper of mine that was related to this, where I had a student who had the same kind of experience. He said he felt like math welcomed him and was compassionate to him. Like that, it wasn't just that he was experiencing or exhibiting compassion for other people by how he was teaching math or something, but like math itself felt compassion in an interesting way. And so I remember, I thought, well, he invited me to talk about this at some point, and I thought, well, maybe it would be a good idea to talk about this example where the student had presumably an analogous kind of experience to what you're talking about. Because there's a way in which it's not just always about having a successful classroom experience with mathematics or not, where you feel like the community is being compassionate to you or something. But in fact, the subject could be by the way that you're able to understand and relate to it, like mentally. So I'll start with this question. I surveyed, so it's an old study, the very beginning part that I want to talk about. Oh, Irfan, I just was talking about you. So here it is. So I was talking about, just very briefly, I was mentioning about the subject of mathematics itself, welcoming or rejecting you, based on the ideas that you encounter when you're looking at the subject, and how your imagery relates to those ideas. Excuse me. So my first question for you is this. What's your guess about the percentage of calculus students out of 350 that I surveyed, how many of them said that it is true that it is possible to choose two different points on the real number line that are infinitely close to each other? A rough guess is fine. Just curious.
Probably a lot, I would say.
You think a lot?
I would think a lot. No, but they wouldn't understand necessarily what that means.
Right. What do they mean
might
by
just
it?
say
That's a different question. That's right.
Yeah.
That's right. But you think it might be, do you think it's more than half of the students?
I would
possibly?
have guessed, my first guess would be because they heard things like that a lot. But
Okay.
yeah. But
yes,
I might be
the
wrong.
answer, in fact, is 87% of the people I asked
Wow, yeah.
answered on the survey. I mean, they said true. And that's when I thought, well, okay, I really need to understand this. Like, what on earth do students mean by this? So I did actually a study, as part of the study, I followed up with a bunch of students by asking them, did interviews with handfuls of them, and asked other survey questions that relate to it. So there's a handful of different kinds of things that students seem to mean, the images that they have in mind when they're thinking about 2 points on in the continuum on the number line that are infinitely close to each other. One thing they might mean is just it's pretty small. So I had one student that I interviewed. She explicitly said that the points 0.001 and 0.002 were pretty close, but not infinitely close. But 0.0001 and 0.0002, she provided those as examples of points that were infinitely close. So infinitely for her was like, there's a threshold, and once you get smaller than that, then she uses the word infinitely to describe how close those things are. So that's one kind of class of thought about it. Other students seem to have an idea that points can be like approaching each other. They're not really static things. So 2 points are infinitely close if you can kind of make one get closer to the other one by means of, usually their decimal expansions are a lot of what students think about. So they might say something like 0.9 repeating is getting closer to 1. So it's infinitely close because it's approaching. But that's not the same as actually it being like all kind of itself already infinitely close to 1. So
Or-
the
or-
student that I have is thinking more like that, yeah.
Or for that matter, being one, just another name for one.
That's right,
which is-
being one, and of course, this is what they're supposed to think, is
Right.
that 0.9 repeating is the same as 1. They're different representations of the same number. But a lot of students don't think this way. Most people that I ask don't actually think that way, especially about those. But that's weird. I don't know why that happened this way. Well, anyway, I wanted to have a little, wanted this to show up not quite like that, but here's how it is. So just pay attention to the top for now. I asked this one student to give me an example of two numbers that were infinitely close to each other. She said 3.9 repeating forever and 4. And I was asking about, well, okay, what does that mean? I wanted to figure out what she's talking about. So one of the questions I asked was, can you think of another number that's infinitely close to both of those? She said, well, sure. 3.999 to infinity plus an infinitely small number. So now already I know that she's a little different from some of the students. Like actually the person sitting next to me on the plane when I was flying out here, like she was like, oh, what are you working on? Oh, this talk. So I asked her about the same thing. And she thought 0.9 repeating and 1 were infinitely close to each other, but like they're next to each other. There's not something else in there. They're like two pearls on a string or something maybe. But that's not what Sarah thinks. Sarah thought that you actually have other small numbers in there between them. What do you mean by that? So I asked how close they were. She said 0.0 repeating infinitely with a 1 after that. And she was very explicit that there are infinitely many zeros in that expression. I said, well, and then she said, I mean, there is numbers, because no matter how small you get it, there's still going to be some kind of space. And even in that tiny, infinitely small space, you could still cut that into infinity too, and put numbers in there. So I'd say yes, but I don't know how to express that. Of course she doesn't know how to express. How do you express that? But her image of it is that. So she's generalizing, actually, I think, and I've done a bunch of later studies with other students about things like this. I think what they do is they're generalizing something from the finite realm, and they're projecting that to their image of what happens at the infinitely small realm. And usually with the idea of zooming in lets you see what's happening there. So, so she would write, so I said, well, what are some other numbers in there? Like, what do you mean? And so she wrote this in terms of distances. So she kind of switched back and forth between distances between 0.9 repeating and 1, and then actual locations, points. So she said, well, the distance between those might be 0.0 repeating infinitely with a 1 after it. But you have other numbers that might be even closer, and the distances there might be 0.0 repeating forever with a 0 and then a 1. And so I asked her all kinds of questions about this. Just following up, I have sound, but maybe I won't play that right now. Of her describing it. I bet I'll summarize for you. And she said, well, yeah, you can keep doing this. And I asked how many numbers are in between here and here. She said, an infinite amount of infinitely small numbers live in there. I asked what happens if you square this number, this 0.0 repeating with a 1 after it. And she said, then you get 0.0 repeating with infinitely many zeros, and then infinitely more zeros. This is amazing, and then a 1. That is super interesting, right? Because if you square like 0.0001, you're going to get 0.0000001. So if you square 0.0 infinitely many zeros and then a 1, you're going to have 2 sets of infinitely many zeros in a row. Actually, Cantor's ordinals are helpful for making that's omega times 2 as a string. So she can situate these on the number line and talk about how they relate to each other. All of them are infinitely close to each other. Oh, that actually is.
Oh, okay. And so with that number, now how would they relate to each other compared to 0? Where would you put both of these two numbers?
This one would just be a little bigger than that one.
Okay.
I think of it like those numbers are the same as regular numbers, you know? But they're still, you can never do that, so that's why it's called infinity.
Okay, okay. So would you say that you can have like, would you say that it's true that you can have infinity and infinity plus 1 and infinity plus 2?
Mm-hmm.
Okay.
But it's still infinity. But you can add that.
Okay.
I asked her all kinds of strange questions about this. So I kind of made a little chart that summarizes her system. The real numbers have finite, infinitesimal, and infinite numbers because she realized, or she decided, or whatever, reflected, that if you take the reciprocal of any of those numbers, you get an infinitely large number. So if you take the reciprocal of 0.0, infinitely many zeros, and then a 1, you get an infinitely large number. If you take a reciprocal of 0.0 with infinitely many zeros, and then another infinitely many zeros, and then a 1, then you get an even larger infinite number than the other reciprocal. There's infinitely many of all of these. If you square, as I said, if you square an infinite number, you get another infinite number. You can divide an infinitesimal infinitely many times. That might be a little small here, sorry. The reciprocal, yeah, that's what I said already. Infinity is different from infinity plus 1, etc. That's a little summary. You can't see the difference between two infinitely close numbers until you zoom in infinitely. At this scale, it looks the same as the original number line if you zoom in infinitely. But they won't be called the same numbers. So she doesn't really have a way of I mean, she's developing a way of notating them, but she's like, she talks about how she's like, I'm not sure I can write it. She says that there are rational and irrational infinitesimals in every space. I'm not actually sure what she means by that. I wish I had followed up on that more with her during the interview. At the time, I didn't know what was going on. I was like, what the heck? So, yeah, and then numbers have unique decimal representations for her. So 0.9 repeating is not the same as 1. It's a different thing. I think it's kind of interesting to look at the way Leibniz thinks about, or thought about, infinitesimals, because a lot of these things, now Leibniz had a different notation than a lot of different things, but Leibniz number line also contained, as far as we can tell, well, this is complex, but this is up for debate, but I mean, he certainly talked about his techniques of developing calculus where he had infinitesimal and finite and infinite numbers as well. And he had different scales of them as well. So with all of these things about squaring an infinitesimal, you get another one. So he talked about how do you square infinitesimals. You square infinite numbers to get another infinite number. You can divide infinite. So these are all the same kinds of things. And the idea, he says if you zoom in on part of the continuum, it'll look like a microcosm of the whole number line. So they're worlds within worlds within worlds. Endless degrees of infinity. He talks about an infinitesimal as a useful fiction. So what is it? Is it another question? So very briefly, we of course now know you can formalize calculus using Abraham Robinson's hyperreals. So nonstandard analysis is this, and the transfer principle tells us that all of the sort of first order logical statements that you can make that are in the hyperreals are true in the hyperreals as well as in the reals, and vice versa. So the transfer principle is kind of the deep idea that connects, that allows us to do calculus in either of these, either of these continuums. I want to mention a couple of things about Sarah. Like, this isn't a whiz kid calculus student or something. She isn't like, it's not like she's heard about the hyperreals or something. This is just her image of how she thinks the continuum looks. But she's explicit about how, like, I know this is wrong to think this way. I know I'm not supposed to. She actually said to me, like, she's like, I know, I just learned in my calculus class. I mean, I've been learning in my calculus class that, like, 0.9 repeating is equal to 1. But, like, that's not how I think of it. It doesn't make sense to me that way. So she says, this is just my crazy way of thinking, and I know this is wrong, but, and she kept saying stuff like that throughout the interview. But yet her system was not just cognitively coherent, but was also mathematically coherent and consistent, and could be developed into a mathematical system that is, if we follow what we know about the hyperreals, as powerful as the standard system. So, but she said her experience of math is different, which was that learning math is just memorizing stuff so you can do well on the test. And she was getting a B- in her calculus class at the time. She didn't connect infinitesimals at all with derivatives or any of the things in calculus. Like it was a completely separate thing for her. So it was a derivative was just a way of calculating something algebraically. So anyway, yeah, she had never seen any. So I was kind of interested in this. I'm like, well, we're not only not on, like, her experience is she has a weird idiosyncratic way of thinking that she thinks is wrong, but she is interested in it and has probably never been allowed to talk about it or pursue it in some sort of class. Certainly is not a support for her learning of calculus. And so I thought, based on this, and I've got maybe 1 minute left, but we'll have a discussion later on. Based on this, I actually made a calculus class that is taught through infinitesimals, because I thought it'd be kind of interesting for students who are like Sarah to be able to pursue and learn calculus and connect the representations in calculus with their own imagery about the real number line. Now, I'm not the first to do this. Actually, of course, Kiesler has a textbook about this. Other textbooks, there's actually quite a few people now that have been doing this. I'll just mention very briefly, here are some of these different approaches that where people have been teaching calculus with infinitesimals and with differentials. Sometimes those differentials, like dx and so on, are not explicitly infinitesimal, but yet they're quantities rather than sort of shorthands or of other things. So maybe I'll come back to this too, because a question that I had here was, if a student is evaluating an interval like this and they do a substitution, what do these equations mean for the students in a calculus class? I think students aren't supposed to believe that differentials are quantities in a regular calculus class, but yet they're supposed to operate like they are. So can we give them a calculus class where those things actually reflect infinitely small quantities, which might fit with the imagery they already have about the continuum? So maybe I'll pause here because it's time for the next talk. And we'll talk in an hour with a discussion, so we'll save up, I guess, questions.
Half an hour.
That's all right.
We'll talk in half an hour.
Half an hour? I thought it was at 10.
No, well, there's only one more talk.
Oh, and so at 9:30?
Yeah, 9:30. Yeah.
Oh, great.
Yeah.
We'll come on down. I'll switch the screen.
No worries. Thank you.
Thank you.